Now, Kirchhoff's loop rule is going to be important when we start analyzing circuits. We'll come back to it again. So let's talk about a conductor in electrostatic equilibrium one more time. Okay, now here I have a conductor. If it's in electrostatic equilibrium, then all the charge on the conductor is along the surface. Okay? So just to remind you, all the charge is on the surface. So if I was at a point 1 or a point 2 inside this conductor, the difference in electrical potential between the 2 points would have to be 0 because there is no electric field in this region of space. There's an electric field starting at the surface going out, but there is no electric field inside. Remember, if there was an electric field inside, then there would be charges that, if there was any charge inside here, i.e. the electrons, they would have to move in response to the electric field. And there's not an electric field in here. All excess charge is on the surface. Okay? So, all excess charge is on the surface. The surface then is an equal potential surface, and the electric field inside is 0. The interior all has the same potential. Okay? So there is no change in electrical potential from any 2 points inside here. The exterior electric field is always perpendicular to the surface, and the surface charge density changes with shape, and so the electric field strength is sharpest. The electric field is strongest at sharp turns where we have the largest density of charge. So, equal potential surfaces close together are going to be larger electric fields than those that are further apart. Now, let's look at these 2 oddly shaped electrodes. Okay, so this would be essentially our negative electrode. So, negative electrode. This is our positive electrode. Now, I know that because the electric field lines are pointing away from the positive toward the negative. Now, if we think about the green dotted lines here, those are our equal potential surfaces. What I want you to notice here is in close to the object, the shape of the equal potential surface is close to the shape of the object. Okay? Mimics the shape. But as I get further away, because these 2 are weird shapes, notice how the equal potential surfaces start to distort. So the field lines are always perpendicular to equal potential surfaces, and equal potential surfaces, okay, their shape is close to the shape of the electrode when you're in close, and they gradually change shape from one electrode to the other. Now, capacitors. Okay, we've been talking about parallel plate capacitors, but we're going to dive into them in a little bit more depth. Capacitors are going to be devices that we're going to use to store energy by way of charge separation. Remember, it took energy, work, to separate the charge. Okay, either by a mechanical means or by induction, but it took work. So a capacitor is charged by being attached to a potential source, like a battery or a Wimshurst machine, that moves charge from one plate to the other. When I have separated the charge then on 2 different plates, I have stored energy, kind of like taking water up a hill. If you take the water up the hill, you've stored energy and it can run down, okay? As charge is being loaded up on the plates then, a repulsion between like charge happens until we essentially reach a limit. A capacitor can be charged only up to a certain point. And at that point, okay, there's a pushback from the charges that are already there. There's repulsion against any more charge being added to, and that's called fully charged, okay? We talk about something called capacitance. Capacitance is a measure of how much charge can be transferred per unit potential, okay? So capacitance, C sub O, is equal to Q, the amount of charge that we can load up, divided by delta V of the capacitor, the electrical potential we have put across it. So it's epsilon 0 times A, the area of the capacitor, divided by D, the separation between the plates. Okay? So C is equal to Q over delta V, or it's equal to epsilon 0 A over D. Now, capacitance is measured in units of farads. 1 farad equals a coulomb, remember, which is our unit of charge, divided by a volt, our unit of electrical potential. So the above equations points out that capacitance of capacitor depends on the geometry of the capacitor plates. Okay? So it depends on the area of the plates, the separation. And then that controls how much charge per unit potential you can put on the plate. Okay? Now, capacitors in combination. When we talk about circuits, we refer to circuit components as either being in series or parallel, like I showed you with the battery. Series means you pass through each on the way back to the starting point. So one after the other. Components are in a line. Parallel means that you can pass through one component without passing through the other on the way back to the starting point. So they look like the rungs of a ladder. They're side by side. So series is in a line, parallel side by side. Now, we're going to represent capacitors with parallel lines and lines coming in. Okay? Well, quite often, let's say if I wanted to represent some capacitors in series, I could draw them like this. For right now, I'm just going to draw my battery like that. Okay? If I wanted to draw them parallel, it look like this. So I could leave this battery and come up and I could go through this way, kind of circling around, or I could go this way and circling around. Here, I have to pass through this one and this one to get back to where I began. Okay? So, when we have several capacitors in combination, we would like to know what the combination capacitance would be. This is called equivalent capacitance. It's the capacitance of a single capacitor that could be used to replace all the capacitors you're using. Now, they make capacitors in standard sizes. Sometimes we need odd capacitances. So we need to know how we can combine capacitors of kind of uniform sizes to get the capacitance that we want for a circuit. Okay? For a parallel capacitor, so parallels meaning side by side, the equivalent capacitance is just the sum of the capacitors. So that means that if I were to have two capacitors here, okay? And let's say this was a 1 microfarad and this was a 10 microfarad, then C equivalent would be 1 microfarad plus 10 microfarads, which would be 11 microfarads. Okay? Now, when these two capacitors are in parallel with each other, delta V between those 2 points is going to be the same. They've got the same voltage. Okay? And the total charge separated is the sum of the charges. So Q1 plus Q2. It's essentially like building a capacitor that's just got larger plates. Okay? So what I've done is I've thought about combining them into just one large plate. Now, when we add capacitors in series, it's a little different. Okay? When I add capacitors in series, if this is a plus Q, then this is going to be minus Q, and guess what? This will end up being plus Q, and this will end up being minus Q. Okay? So the charge on all the plates are going to be the same. The Q equivalent is just going to be equal to Q1, which is equal to Q2, whatever the charge is. Now, if you think about this, then if this is a delta V between this point and this point, then some of the electrical potential drop is across this capacitor and some of it is across this capacitor. Turns out that 1 over C equivalent is equal to 1 over C1 plus 1 over C2 for every many capacitors you have. So if this was a 10 microfarad capacitor and this was a 20 microfarad capacitor, then C equivalent would 1 over C equivalent would be 1 over 10 microfarads plus 1 over 20 microfarads. So let me do that. 10 1 over plus 20 1 over. So I get 1 over C equivalent is equal to 0.15. To get the equivalent capacitance, I'm going to say C equivalent is 1 over 0.15. Okay? And so 0.15 1 over gives me a capacitance of 6.7 microfarads. Okay, microfarads. Now notice, when I put things in series, I end up with a capacitance that's smallest than the smaller capacitor. When I put things in parallel, I get something that is larger. Okay? Now let's look at a problem where we've kind of got some combinations of things. We're going to look at problem 56. Okay? So if we look at problem 56 here, actually, I like problem 57 better because that gives us a little bit more practice. We look at problem 57 here. We've got a 9-volt battery, and then we've got a 4 microfarad capacitor, a 12 microfarad capacitor, in a 2 microfarad capacitor. Let's see if I can get it to focus in a little bit. There, that looks good. Okay? Now, when we look at this, you can think about this as coming in and it hits 2 capacitors that are in parallel with each other, and then it comes to a capacitor that this combination is in series with. So I'm going to look at combining those 2 first. So let's scoot over here. Okay. So if I think about the 2 that are in parallel, I can just as easily draw it like this. Okay, so this is a 4 microfarad, and this is a 12 microfarad. They're in parallel. So I can replace those with a single capacitor that's just the sum of those 2. 12 plus 4 is 16 microfarads. And now I have a 16 microfarad in series with a 2 microfarad. So if I want to take this down to 1 single capacitor, then C equivalent C equivalent is going to be 1 over 16 microfarads plus 1 over 2 microfarads. So 2 1 over plus 16 1 over. This is 0.5625 over microfarads. So C equivalent is 1 over, well, 1 microfarad over 0.5625. And I get 1.8 microfarads. Notice the equivalent is less than the smallest capacitor that we had in series. Okay? All right, let's scoot back over. Okay. Now you can try 56 and 58, they're just kind of on the same thing. Okay. Energy stored in a capacitor can be calculated in a few ways. Okay. The electrical potential energy for a capacitor can be thought of as 1/2 times the capacitance times delta V squared, or it can be Q squared over 2C, or it can be A, D, E squared epsilon 0 over 2, depending on what information you're given. Okay? Now, one of the hot topics with batteries right now is energy density. What volume of space do you have to store how much potential energy? So, the energy density is equal to the electrical potential energy for the capacitor divided by A times D. A, surface area of the capacitor, D, the separation between the plates, that gives you a unit volume. That's why it's energy density. Or it can be thought of as epsilon 0 E squared over 2. Okay? So let's look at problem 31 in the textbook. So let's look at problem 31. See if that's still what I want. Let's look at problem 31 here real quick. Okay? It says, what is the potential, to what potential should you charge a 1 microfarad capacitor to store 1 joule of energy? So U is 1 joule, and the capacitance is 1 microfarad. Okay? Now let's look at our equations again. We're given U and we're given C, and we're asked delta V. It asks us what potential. So we're going to use this first equation. Okay? So we're going to use this guy. So I'm going to work it over here. So if I plug in, I have 1 joule is equal to 1/2 times the capacitance, which is 1 times 10 to the minus 6 farads. Okay, because it was in microfarads, delta V squared. So it's going to be 1 times 2 divided by 1 exp6 negative. So I have, well, 2.00 times 10 to the 6 joules divided by farads, which is a volt, is equal to delta V squared. So I just take the square root of that, and I get delta V to be 1.41 times 10 to the 3 volts. Okay, it's just a plug and chug problem. Chapter 30, problem 31. So we're giving U is 1 joule and C is 1.0 times 10 to the minus 6 farads. Okay, not too bad. Okay, now, when building a capacitor, we know what charging the space, when changing the space, changes the capacitance. But there are other ways besides just changing the spacing between the plates of a capacitor to change the capacitance. And one is to add a dielectric. It's a material that we put between the plates instead of leaving it as a vacuum or empty space. Okay? Now, the presence of a dielectric always increases the capacitance of a capacitor. Okay? A dielectric is an insulator. All right? And when an insulator is put between the plates of a parallel plate capacitor, it will polarize. So, let's see. So if here's the plate of a parallel plate capacitor. So this is negatively charged. This is positively charged. Okay? If I come in here and I put in a dielectric, what happens is this side becomes positively charged and this side becomes negatively charged. Okay? So that's what the dielectric is going to do. It's going to polarize. So that was our negative plate or positive plate. This guy polarizes. Now, since it's polarizing, okay, the electric field from my original plates point this way, right? The electric fields for my dielectric point in the opposite direction. Okay? If I have these two electric fields in this region of space pointing in opposite directions, they add together to give me a smaller electric field. So to get up to the electric field based on the voltage that I can put onto these plates, I'm going to actually have to put more charge on those plates. Okay? So, we know that the capacitance inside a capacitor with no dielectric is Q over delta V, or EA over D. We add in the dielectric, okay, which is polarized and creates that field in the opposite direction. Okay, like here. There's the original electric field. There's the electric field caused by the charge separation inside the dielectric. Okay, the net electric field. K for the dielectric is the dielectric constant. It's the electric field if there was no dielectric divided by the electric field when the dielectric is present. Okay, vacuum has a dielectric constant of 1. Doesn't do anything. Air, pretty close to 1. Okay? Teflon, 2.1. Polystyrene, 2.6. Mylar, 3.1. Paper, 3.7. Plexiglass, 4.7. Pure water, 80. Titanium dioxide, strontium dioxide, so on and so forth. Turns out the capacitance of a capacitor with a dielectric is K times C0. What it would be if there was no capacitor, no dielectric in there. Okay? So, we have the dielectric constant and the dielectric strength. So what the dielectric does is it allows us to pile up more charge on the plates of a parallel plate capacitor. Okay, so let's look at problem 35 at the end of the chapter. It says 4 by 4 centimeter metal plates are separated by 0.2 millimeter thick piece of Teflon. So I've got a plate that's 4 centimeters by 4 centimeters, and the plates of the parallel plate capacitor are separated by 0.200 millimeters. And we want to know what the capacitance is. And we have Teflon. All right, now I've written that down. Let's go back to looking at our equations. All right, so let's scroll down here a little. Number 1, we're dealing with Teflon. So our K is 2.1. Now, come on. Let's talk about calculating the capacitance. C0 is going to be epsilon 0 times A over D. I'm calculating it based on the geometry of the capacitor because I haven't been told Q or delta V. So let's go back up here.
You're looking busy this early in the morning.
I am.
Everybody doing well?
Sorry guys, got interrupted, but we're looking at problem 35. Okay, and so we're going to use, where did I put my pen? There it is. First thing we're going to do is we're going to use C0 equals epsilon 0 A over D. So epsilon 0 is 8.99 times 10 to the minus 12. Okay guys, I am going to get this chapter finished, I promise. To calculate the initial capacitance of the capacitor with no dielectric, it's going to be E A over D. And E, remember, epsilon 0 is a constant. Okay? And the value for that is, the value for epsilon 0 is 8.85 times 10 minus 12. I thought that looked wrong. Let me erase here real quick. Okay, so 8.85 times 10 minus 12. There's the area, and the separation is 0.2 millimeters. So that's 2 times 10 to the minus 4 meters. Okay, so if we calculate that, 8.85 exp12 negative times 4 exp2 negative squared divided by 2 exp4 negative says the capacitance is 7.08 times 10 to the minus 11 farads. Don't be freaked out by a small number there. We'd expect a small number because most capacitors have small capacitances. So C should equal K times C0. So I take 2.1 times 7.08 times 10 to the minus 11 farads. So that's 1.49 times 10 to the minus 10 farads. So that's 0.149 nanofarads. Okay, not a hard problem. Now, some problems that you might want to look at the end of this chapter. You might look at conceptual problems 4, 6, and 12. And there's end of chapter problems. And that is the end of this chapter.